Okay, so hopefully that animation gave you a little bit better idea in terms of like what's physically happening, but now let's go into the mathematics of it. So I do want you to draw this out. So this is kind of our standard double slit experiment where we have one interface here where I have the two slits, and then here is my second interface. This is actually going to be my screen where the light waves are going to strike. And let's kind of just define some things here. So D is the distance between the slits, so that is going to be like physically this slit separation. L is the length between my slits and my screen. And X just is representative of some point on my screen from the center point. So if I put like right here, like this would be my X value, okay? Now, recall that whether I'm going to have constructive or destructive interference at this point depends on the path length difference between what comes from this slit versus this slit, okay? So this would be like L1, and this would be L2. And if I'm thinking about this, another kind of way to visualize this is if I look at kind of like the average here, like this angle is some theta value, right? And the path length difference is actually like this extra distance, like that this wave travels this much extra. So that physically is the delta L right there between there and there. And we could model that with a triangle. It's a right triangle. And that, when you look at the geometry of it, and I don't have the time to go into it, but if you look at the fact that if this length is significantly larger than this distance, this angle theta here is the same as this angle theta here. And so this extra length that this guy travels, if this is like a right triangle, here's my theta, this hypotenuse is the distance between the slits. This delta L is equal to d sine of theta. And that represents that extra little distance that one of the waves from the other slit has to travel. And so we know that if this extra distance, if this delta L is equal to an m lambda, then I'm going to have constructive interference. Another way I could write this is d sine theta. D sine theta is equal to m lambda, where m is equal to 1, 2, 3, etc. I will have constructive interference. If this d sine of theta is equal to m plus a half lambda, if that extra little length is equal to m plus a half lambda, I will have destructive interference. And again, we're m. Here the counter starts at 0. And this is why, this is coming back to now why when I modeled it, I think here, this is the 0th dark fringe because my counter starts at 0. And then this is my first order dark fringe because at that point, m is equal to 1, and then continuing on, okay? So this is the relationship to figure out if I'm going to have constructive or destructive interference, okay? Now, oftentimes, though, this angle is really, really difficult to measure. So there's another way that we can model the equation for how do I determine if that extra little bit of distance is going to be a whole integer or a half integer of the wavelength. So I'm going to erase this. I'm going to leave this kind of pictured here because the geometry of that's going to help. So remember that another way we can represent this point in space here is this x value, right? So I could say that I'm going to have, well, I'll do it this way. If I have the fact that my tangent of this angle is equal to opposite over adjacent, so x over L, is another way I could represent like what this position is. Now here's the thing. If theta is small, that's the caveat. If theta is small, and the only way theta is going to be small is if my length is much, much bigger than my distance, okay? If my length between where my slits is much, much bigger than like this distance of my slits, then the tangent of theta is approximately equal to the sine of theta. Okay, like mathematically this is true. If my length is really, really small, if my length is really, really big in comparison to my distance, it makes my theta really small. And if my theta is really small, these two are equivalent. So what this means is, remember we said that we could represent d sine of theta to be our extra length. So sine of theta could equal my extra length over d. But if for small angles, my sine of theta is equal to my tangent of theta, I could set this equal to this x over L. And you get this relationship for the extra length, x times d over L. So if the extra length is equal to an m lambda, then I'm going to get constructive interference. If the extra length is equal to m plus a half lambda, I'm going to get destructive interference, okay? So let me, now I've run out of room. I think I can do this. I think I can, but I don't want to erase that. Oh, golly. I didn't save myself enough room, so I'm going to have to erase this. So again, if delta L is equal to m lambda, I get constructive interference. But if delta L is equal to m plus a half lambda, I'm going to get destructive interference. What we can do is we can rearrange this to figure out what is the x value. Like, what is that physical x distance going to be on my screen where I get the constructive and where I get the destructive interference. And the equation is always modeled for the constructive interference, and if we're looking for the destructive interference, we would add a half, okay? So I'm going to come down here, and I'm going to say m lambda is equal to x d over L, and again, this is for constructive interference. I'm going to solve for x here. So that would mean I'm going to bring the L over and the d under. So x is going to equal to m lambda L over d. So this is where I would get constructive interference. I'll say this, points of constructive interference. If it was a point of destructive interference, it would be x is equal to m plus a half lambda over d. This would give me points of destructive interference. So it's where you could physically measure on the screen, okay, this far away is going to give me constructive, this far away is going to give me destructive, then this far away is going to be the next constructive, the next destructive, etc. Okay? And I know this is heavy lifting right now, and I'm sorry that you had to learn this via online. I'm going to do one example in the online lecture, or the kind of next video, and hopefully that'll make it a little bit more concrete, and then when we come back into class, we'll go over it some more.
Okay, so this is meant to walk you through just two examples of double slit diffraction. So this first one says that suppose you pass light from a helium neon laser through two slits separated by 0.01 millimeters. So that is the D, that's the slit separation. And you find that the third bright line on a screen is formed at an angle of 10.95 degrees. So that's the theta. And it's the third bright line. So that means M is equal to 3, and it's a bright line. So it is constructive interference. And it is asking to figure out what is the wavelength of the light. So we're trying to figure out what the lambda is. And we know the distance is 0.01 millimeters. So that's times 10 to the negative 3 meters. And we know that our theta is 10.95 degrees. So one of the relationships we have for interference pattern for double slit experiments is that d sine of theta is equal to m lambda. And in this case, we know our D, and we know the angle is 10.95 degrees. We know this is the third bright line, so my M value is going to be equal to 3. And we're trying to figure out what the wavelength is. And so if you were a studious student, you would pause the video, you'd get out your handy dandy calculator, you'd calculate what the wavelength is, and you should get 6.33 times 10 to the negative 7 meters, which is also 633 nanometers, if you, because nano is 10 to the negative 9. Okay, let's try one more. This says in a double slit interference experiment, the distance between the slits is 0.005 meters, so that's the D. And the screen is 2 meters from the slit, so that's the length. That's the distance between where the double slit is and where we're seeing our bright and dark spots. And yellow light from a sodium lamp is used, and it has a wavelength of 5.89 times 10 to the negative 7 meters. So my wavelength is 5.89 times 10 to the negative 7 meters. And it wants to know what is the distance between the first and the second fringe. So remember the interference pattern, like bright spot, brightest spot, that's essential, dark spot, bright spot. Okay, so it's wanting to know what's the distance between the first and the second fringe. So if this is the 0th order. Okay, so this is the first fringe, bright fringe. This is the second bright fringe. So it wants to know what is the distance between those two. And so what we will need to do is we'll figure out what is x1, what is x2, and then subtract them. Okay, so our general equation for constructive interference for a double slit experiment, xm is equal to m lambda L over the slit separation. So for x1, that's going to be 1 times my wavelength of 5.89 times 10 to the negative 7 times my L of 2 divided by my distance, which is 0.005. And then same process for x2. So this would be my m value, though, is now 2. So this is going to be 2 times 5.89 times 10 to the negative 7 times my length of 2 divided by my slit separation of 0.005. Big truck going by. So again, you should pause the video, calculate out what is x1, what is x2. I'm actually not going to give those values to you. I'm going to expect that you should calculate them, but you should expect that the difference between the two is 0.00235. Okay? So you should be able to calculate out what this value is, and subtract that by. So those are two examples of using the equation for interference for Young's double slit experiment.